All right, thank you. Thank you, Andy. Well, good afternoon, everybody. Welcome. This talk is called MLOps with Azure Machine Learning and Mlflow. I will be talking about machine learning, but first, let me introduce myself. My name is Floris Berends. I'm a data scientist with InSpark. My job includes working with machine learning models on the Oxygen data platform that we provide as a service to our customers. Such, I deal with developing machine learning models and making sure that they make it into the production environment. So today I will be talking about machine learning. I will not be talking about how to train your model or how to optimize your hyperparameters, but instead I will be talking about implementing machine learning on a data platform and the challenges that are involved in doing so. I will talk about MLOps, Azure Machine Learning, and the Mlflow. After this talk, I hope to show a little bit, give a short demo, and I hope that you will have learned a little bit about how to implement machine learning on a data platform. Andy will be monitoring the questions in the chat. So if there's anything that you want to ask, just post it in the chat. So first off, why do we actually need machine learning? Well, we can use machine learning for a variety of data processing tasks that would otherwise be complicated or time-consuming. Think of like forecasting sales or estimating the optimal price of a service or a product. You can do this using a script, but most of the time it's more efficient, faster, or less work to just use machine learning. So most of you will at least be somewhat familiar with how these models are developed. You take a lot of data and you put it through a machine learning algorithm, and then you fit a model using the training algorithm. And just doing this on your laptop or within a single notebook, that's fine and all. But if you want to do this on a data platform, then you require a process for doing this repeatedly, and that's where MLOps comes in. MLOps is the process of managing the machine learning lifecycle and all the assets that are involved. So now I want to talk about MLOps a bit. A simple way of describing the machine learning lifecycle looks like this. You just train your model and you deploy it, right? Couldn't be simpler. Well, it actually looks a little bit more like this. It's repeated development cycles that feed into each other. You have to ingest your data. You have to prep your data for training. You have to train your model, deploy the data, deploy the model for consumption, and you have to monitor the entire cycle. There's also not a clean border between these processes. Often you'll find that you'll need more data once you begin training your model, or that you need other features or more features, and that you need to go back to the previous cycle. Each of these cycles involve a lot of challenges that we have to overcome. So I want to talk about these challenges a little bit. Machine learning lifecycle begins with data ingestion. Data resides in a remote storage solution, but you need it for analysis and integration. So getting data from a variety of storage solutions means that you'll have to use many ways of loading the data, and you also need many different authentication methods. Managing authentication for a lot of different sources is a challenge because you need to store the credentials somewhere safe. But with machine learning, it's also very important to know exactly what data was used to train a model. That's because a specific model is very dependent on the data on which it was trained, and it's therefore necessary to version your data sets and keep track of what data was used to train what model. So for data ingestion, we have two challenges: managing our data sources and managing our data sets. So once we have our data, we need to prepare it for training. And data prep is needed because enterprise data sets are rarely out of the box ready for training a machine learning model. It includes transforming data to fit a certain schema, but also resolving data quality issues such as missing data. But it also involves feature engineering. And feature engineering is when you compute new data columns to benefit your model. An example might be that you're training a forecast model and decide to include a Boolean column that encodes a specific holiday. So yes for Christmas, no for no Christmas. This is necessary because most machine learning models require a certain relationship between the target and the features to be explicit. Some machine learning models require more feature engineering than others, but data prep is almost always necessary. The prep itself usually consists of code, and as part of the code, you're probably using third-party software libraries. Software requirements are referred to as dependencies, because in order to execute the code, you depend upon the availability of the software. Now, having these libraries available to you during development, but also during production, requires that you're able to package and manage these dependencies. And finally, with large data sets, these transformations aren't executed on local compute resources. When you prep a small data set locally, none of this is an issue, but handling a lot of data or just handling data securely requires that you have remote compute resources. Running transformation jobs on remote compute enables you to scale it up when you need more storage or more processing power, but it also ensures that the data never leaves the platform. When you handle these data sets locally, then you have a local copy of the data. That means it's a security risk. But this does, however, mean that you have to manage the remote compute resources, making sure that they're available, making sure that you're able to send the transformation code and have the software dependencies installed on the remote compute as well. So this leaves us with 3 additional challenges: managing the data transformation code, managing the software dependencies, and managing the remote compute resources. Well, once we have the data and we have our big computer clusters, we're ready for training. And some of these challenges are similar. Model training is also something that requires third-party software libraries, and you also need remote compute resources. The big difference with data prep is that a lot of data preparation can be done interactively. You can write and design the data transformation and then execute it, see the results directly, see the impact on your features and on your columns. But for model training, this usually cannot be done. Training often takes a while, especially with large data sets. It's therefore necessary to be able to evaluate your training results based on the input parameters. And you can do this by keeping track of metrics that are computed during the calibration of a model. For example, training a forecast model might show you the reduction in error while the model is training, and the final accuracy and error metrics determine if a model performs well and indicate whether to keep the model or go back and include additional features. Sometimes it's necessary to just try a bunch of different parameters in parallel and see which model worked best afterwards. So doing this, it requires that you have a setup that allows you to easily train models and track them over time and see what works and see what doesn't. Once you've trained a model, you usually end up with a binary file that includes the model core and its weights. And in order to use this model, you need this file, but also the software libraries that you use to produce it. You'll also need a scoring script that takes the input and transforms it into the output that you desire. If we're talking about a forecast, it's the time series plus the value that you're forecasting. And all of these things together make a model package. It's everything you need to use your model back together. You don't have to do this for all the models that you train, but if you're planning on using the model later, packaging a model in this way saves you a lot of time. Well, finally, versioning your models is equally important as versioning your data sets and versioning your code. Figuring out why a certain model is faulty or underperforms or performs really well is something that's very important. And it's a lot easier if the models are versioned. This way, during model consumption, you know what specific model you're using and make sure that you can troubleshoot when things go wrong. So model training presents us with three new challenges: having a repeatable training setup, model packaging, and model versioning. So once we have our models, we want to start using them. Like I mentioned before, you need a model package in order to use the model. Making the model package available for model consumption is what we call deployment. So there are two main different ways to deploy a model. You can deploy it as an API so that other services can call it over HTTP. That's good for fast and live results. For example, ChatGPT is an example of a model that's been deployed with an API. You can just send your data to it and get results back immediately. Another way of deploying your model is to deploy it within a pipeline or workflow that runs on a trigger. So either on the schedule or on an event. That's good for batches. So let's say you have an integration pipeline and you're using a machine learning model within it that runs daily. That's an example of a model deploying within a pipeline. So deploying a model package as an API requires that we have a deployment target. This could be a web server, or most likely a Docker host or Azure container instance. If anyone's unfamiliar with Docker, Docker is a way of taking a software application and running it on a miniaturized operating system. It's probably Linux. And a Docker container refers to that basic operating system that has your software application installed on it. A lot of different web services like Azure, but also AWS can run Docker. And for machine learning, Docker is a straightforward and easy way of taking a model package and its software dependencies and then running it as an API so that it's able to service requests. Apart from having an API like this, having a pipeline or workflow that can run your model is also very handy. This only requires that we make the model available to an existing tool like Azure Synapse or Databricks or even SQL Server. Although there are some compatibility issues that you have to overcome. You have to format your model in a certain way, but as long as we have a pipeline that can run our model, then you don't have to deploy any additional resources. Finally, if we are deploying our model within a production environment, then we need to have a process for updating the model with new versions as they come along. Specifically, when there's a need for a new version of the model, then we need to be able to switch out the old model with the new version. So for model deployment, we have these additional challenges: managing our deployment targets, containerizing our model package, and making sure that we can update our model when new versions come along. So finally, monitoring is key to managing any software platform. So for machine learning, this means monitoring your pipelines, monitoring endpoints and compute resources, but also your data sets. We've already talked about pipelines a bit. You can have pipelines for transforming your data, for training a model, but you can also have pipelines for consuming your model. Sometimes these fail, and you need to know why. So logging during pipeline execution and monitoring your pipelines is very important. Of course, interactive development is almost always preferred over running a pipeline and having it fail, going over the logs, adjusting code, and then retrying your pipeline. But machine learning jobs are long-running tasks, and sometimes you just have to wait for the task to finish. So logging and monitoring your pipelines is key. For endpoints and compute resources, they need to be monitored to ensure service health. If you're running machine learning endpoint in a production environment, you need to be able to know that it's live, that there is backups, and you need to be able to tell when things go wrong. So monitoring ensures that you can optimize all of these resources. Now, of course, data, it changes over time, and this will impact your machine learning models. especially if your model is calibrated for historical data. It might lose accuracy because the data has changed. This is called data drift, and it can be monitored as well. So at the end, we're stuck with a machine learning lifecycle that looks like this. A lot of challenges that we have to overcome. So now I want to talk about Azure machine learning a bit and see how it approaches all of these challenges. So Azure machine learning. What is Azure machine learning? Azure machine learning is a Microsoft product. It's hosted on the Azure platform, and if you're not familiar with Azure, it's the Microsoft cloud, and you can use Microsoft resources available on the platform through a subscription. Any resources that you use are made available to you by deploying them within your subscription, and Azure Machine Learning is one of those resources. But in order to use Azure Machine Learning, you need other resources as well, like shown here, Azure Data Lake or SQL databases or storage accounts. Now, apart from this, Azure Machine Learning is a tool for managing all of your machine learning assets. You can use it to manage your compute resources, manage data sets and pipelines and your models. But the platform doesn't host any data. Data that's used by Azure Machine Learning is stored on other Microsoft products like Azure SQL and Azure Storage. And Azure Machine Learning can only ingest data from other Azure storage solutions. So if you want to work with Oracle or SAP data, then you'll have to ingest it on those Microsoft products first. So data ingestion. We had two challenges for data ingestion: managing data sources and managing data sets. And the way that Azure Machine Learning approaches data management is by defining two kinds of data assets: data stores and data sets. Data stores are references to data storage solutions. So a SQL database or a data lake container or an Azure file share. So for each of our data sources, we define a data store, but data stores are also used for target storage. So target storage, it's also a data store. Data stores include the authentication needed for accessing the underlying data storage solution. And there's two methods of authentication that Azure Machine Learning uses: identity-based authentication and credential-based authentication. Credential-based authentication stores the credentials together with the data store, and identity-based authentication stores no credentials at all. So for interactive notebooks, the logged in user's identity is used for authentication, and for automated pipelines, the compute cluster's identity is used. This form of identity-based authentication uses the Azure Active Directory in order to manage access to the underlying data source. So for example, if you're using SQL authentication, that's no identity. If you want to use SQL authentication, you need to use credential-based authentication. Data sets, on the other hand, are references to specific data on the data store. So for SQL, the data store would be the SQL database, and a data set would be the SQL query that results in the final data set. For a data lake, a data set is defined by a path pattern. So for example, we can define a file data set that consists of image files that we want to use for an image recognition project. And then the files are stored in Azure Blob Storage. Storage container will be our data store, and the path on the container will be our data set. In this way, Azure Machine Learning manages all kinds of data assets. You can register a data set and generate profiles for the data set as well. And this way, a registered data set can be referred to by its name and version number. So for a pipeline, you'll have sales data, version 1. And then you can profile the data set and make sure that, okay, so this version of the data set had 20,000 rows and next version had 19,500. So we lost some. And you can keep track of these data sets over time. So having data management out of the way, we can talk about data preparation. And as discussed earlier, data preparation involves 3 challenges. You need to develop your transformation tasks, dependency management, you need to manage your dependencies, and you need to manage your compute resources. So I want to talk about developing your transformation tasks first. And to do this, Azure Machine Learning provides an interactive development environment in the form of notebooks. So a notebook is like an interactive script. Some of you might be familiar with Azure Synapse notebooks or Databricks notebooks. Well, Azure Machine Learning uses Jupyter notebooks. And a notebook is, like I said, it's an interactive script. You can write and execute code in the notebook and then display the results all within a single interface. Code within a notebook is executed by Azure Machine Learning compute instances on a Jupyter kernel. So a kernel is an interactive software environment that can be customized by installing additional libraries. So, like I said before, you're using third-party software libraries in order to transform your data. A list of all these dependencies, that's what your kernel is. It's all of these software libraries together. Compute instances come with a number of these kernels pre-installed on them, but you can add any as you see fit. Within a notebook, you can load your data sets and start developing your data preparation script. You can also start working on training machine learning models right away and compute any metrics that you want for evaluation. Any intermediate files that you generate, for example, you generate a script file or just a configuration file, you can store it on the Azure Machine Learning file system. This file system is separate from the data sets that you work with. So like I mentioned before, for all of your data sources, you define data stores and data sets, but your working directory, for that you have a file system. As soon as you're satisfied with the code that you've written, if your transformation script is done or your training script is done, then you can check it into version control. All of these compute instances come with Git pre-installed on them. So you can just clone a repository, work on your transformation script, and then check your script back into version control. And the notebooks that you work on are also stored on the same file system. So these notebooks are great for interactive development, but for automated and scheduled tasks, Azure Machine Learning provides pipeline jobs. And pipeline jobs are automated machine learning tasks that can be used for training a model, but also can be scheduled for an inferencing job. So you can use these pipelines to produce models, but let's say you have a batch job that you want to run. You can also run this job within Azure Machine Learning. Pipelines consist of a number of components, each of which consists of some code that needs to be executed, input and output parameters. And like I said, components can have inputs and outputs, and they pass these to each other until the pipeline is done. So typically you'll have separate components in a training job, for example, for prepping your data, training the model, and then evaluating your model and registering it to the model registry. Like I said before, the software environment that's used in a notebook is called a kernel, but the software environment that's used in a pipeline component is simply called an environment. The main difference is that a kernel, a Jupyter kernel, is used for interactive development, but these environments are used for automated pipelines. So more on that later. I have a separate slide for discussing the environments. Separating the pipeline jobs into components like this has a number of benefits because it allows for separating the data preparation scripts from the training scripts. As you might expect, you need the transformation script later during inference. So separating this logic has a number of benefits. And individual parts are more easily fixed when they're broken. So when you're debugging a pipeline and you know that one component fails, then you can just go and debug that component specifically. Also, Components can have separate environments, so it helps reducing the number of dependency conflicts that you have, and component metrics can be tracked separately. So for all of the metrics and the outputs that you generate during the execution of these jobs, it's possible to track and register them. Metrics that are registered during the execution of a job are logged and can be retrieved later by looking up the job in Azure Machine Learning. So for all of these jobs, you'll have an overview in Azure Machine Learning, and you can look back at them at a later time and see how they did, when they succeeded, or maybe how and why they failed. The components themselves can also be registered onto the Azure Machine Learning workspace, which is only necessary if you want to reuse the same component. So say, for example, you write a generic train a forecasting model component, and you have a number of different forecasting models that you want to train, then you can reuse the same train a forecasting model component. In this way, you're free to develop the pipelines until you're satisfied with the result, and then integrate these pipelines into your workflow as you see fit. So these pipelines and these notebooks, they run on Azure Machine Learning compute resources. I mentioned that notebooks run on compute instances, and the pipelines usually run on compute clusters. Instances are for interactive development. They are assigned to a specific developer. This is done to provide a customizable development environment that's for a single developer only, so that you don't interfere with other people's development environment. Compute instances are Microsoft managed, so they're virtual machines that you won't have to manage yourself. You won't have to install any updates, and they also won't show up in your subscription. Same is for compute clusters. However, you're able to attach compute resources that you host in your subscription as well. So let's say you already have a VM or you have a Kubernetes cluster, then you can also make use of those compute resources within Azure Machine Learning. So finally, I mentioned environments, and these are needed for running jobs. Azure Machine Learning provides an environment repository where these software environments can be built and stored for later use. As you're developing transformation code and training scripts interactively in a notebook kernel, you can keep track of the libraries you install, and an environment can be built by providing this list of dependencies. So if you're training your forecasting model and you're prepping your data, and you realized, oh, I actually need like NumPy or scikit-learn, you can install this into your kernel, and at a later moment, just put out the list of dependencies that you use and use this list in order to create your custom environment. The most straightforward way of making sure that you're developing your code with the same environment that you're using for these jobs is to just use the same definition file. Azure Machine Learning provides an interface for managing and registering these environments. And a registered environment, of course, is reusable for jobs. So if you have a standard training a forecasting model environment, then you can use this for all of your different jobs. But you can also just provide the conda file, the list file to the job itself, and then you won't have to register your environments. So Azure Machine Learning comes with a number of curated environments as well. So some environments are a bit more complex because there's a lot of dependency conflicts that you have to prevent. Microsoft provides a list of curated environments in order to help you out. So the model registry comes along once we have handled pipelines and compute resources, and we're ready to train a model, and we need to leave it somewhere. So Azure Machine Learning provides a model registry that serves as a repository for your models with some important features that solves some of our challenges. The model registry comes with version control. It allows for storing metadata and artifacts with your model, and it also serves as an interface for other tools. A model can be stored in the model registry together with training metrics, training artifacts like graphs and images. Or maybe you also trained a model explainer to help explain your model. And you can store it together with your model. And this makes the model registry great for storing our model. Sorry, I seem to have had a bit of headset issues. Can you still hear me?
Yes.
Okay. My head just quit on me. Let's see, where was I? Oh yeah, so the model registry. Because we're allowed to store artifacts with our models, this is great for having a model package together with our software dependencies and our explainers and our information about the model. And also, like I said, because it serves as an interface for other tools, Azure Databricks can just pull models out of the registry and start using it within a Databricks notebook or a Synapse notebook. And you can also deploy models directly from the model registry to endpoints, like Azure Container Instances, for instance. Because deployment, of course, depends on having your models available within this model registry. And if we want to deploy a model, we need to be able to have the model package, containerize it, and set up and manage our deployment targets. And Azure Machine Learning provides an interface for setting up these deployment targets and deploying a model package to the targets. There's two targets that Azure Machine Learning provides for you. There's managed endpoints and there's web services. Managed endpoints are Microsoft managed, so they exist within the Azure Machine Learning workspace. And web services are deployment targets that exist outside of your workspace. Managed endpoints are, like I said, Microsoft managed. So Microsoft provides an HTTP path for you that serves as a stable interface for a model API. And you can use these endpoints either by deploying them through the UI or by using the SDK. And as soon as you have your endpoints, then you can deploy your models to it. Web services are Docker hosts that are outside of Azure Machine Learning that you've set up beforehand. So you cannot deploy an Azure Kubernetes cluster from within Azure Machine Learning. You need to set it up before. And then once you have it, you can deploy your machine learning models to the cluster. Because once these deployment targets are set up, the deployment itself consists of the rest of the things we need, the model environment, and a scoring script. If you just have your model, then you need to provide the environment and the scoring script yourself. But if you use Mlflow to package your models, then all of these things are generated for you. So monitoring, that's the final challenge that we need to overcome. Compute resources, pipeline jobs, and data sets, they can all be monitored from within Azure Machine Learning because most of your computes exist within Azure Machine Learning as well. The pipeline jobs are tracked using Mlflow tracking, and data sets can be tracked using a data-driven monitor. But for more advanced logging, you need to set up diagnostic settings and then log through application insights. A lot of the things can be monitored from within Azure Machine Learning, but Azure Machine Learning generates a lot of other metrics and other logs. And if you want to have more advanced logging, then you need to use application insights. For example, inference results for your endpoints and workspace activity, like the creation of compute resources, are then available within application insights. So, in summary, the Azure Machine Learning approach to machine learning operations is to provide data assets for managing ingestion, pipeline jobs for facilitating the preparation of data and training your models, environments for managing your dependencies, having a model registry for training your models and then putting your model somewhere, providing managed endpoints for deploying your model, and Mlflow tracking for making sure that you can monitor your pipeline jobs and package your models. So Mlflow, I've mentioned Mlflow a couple of times. It's an important part of what makes Azure Machine Learning work so well. So I want to explain a little bit more about Mlflow before I demo this entire cycle. So what is Mlflow? As I said, a lot of the tracking that's done in Azure Machine Learning is done through the Mlflow API, tracking metrics and logging artifact and parameters during a run is done by using Mlflow. So Mlflow is an open source framework for tracking machine learning tasks, managing and administering runs, and packaging ML models. What you see right now is just from their website. A lot of machine learning platforms use it, like Amazon SageMaker and Databricks and Google Cloud. It's very popular, and it's a very good framework because of the many integrations. The API supports many popular frameworks like scikit-learn or TensorFlow, PyTorch, XGBoost. And precisely because of this, it's so easy to use. Two things are important with Mlflow. It's tracking and packing. So the tracking and the registry, tracking is important because you do a lot of runs, and storing the information that you generate during a run, it's necessary. And Mlflow tracking allows for the logging and storing of many different kinds of things, like metrics and charts and parameters and artifacts. Azure Machine Learning integrates with Mlflow in order to better visualize and track the metrics and parameters. But Mlflow is the underlying framework that Azure Machine Learning uses. And as you see here, if you have a Mlflow tracking server, then you can use it to track all of your pipeline runs. Azure Machine Learning just serves as a Mlflow tracking server in this way. Databricks also serves as an Mlflow tracking server. And I believe that Azure Synapse also has an Mlflow tracking server running within it. As long as you have a tracking server, you can run your jobs. You don't even have to run the job on Azure Machine Learning. You can also just run your job locally and then point the Mlflow tracking URI to your Azure Machine Learning server, and it will track all of your runs for you. Packing is another important part of what makes Mlflow work. As discussed earlier, for consuming machine learning models, you will always need a software environment and a scoring script for using the model. And Mlflow provides a way of packing a model together with the environment definition files. And this is an example of such a package. The ML model file lists the model signature. So it will contain the input schema and the output schema for a model, so that tools that use the model know what data to put in and how the data comes out. The Conda YAML file here, that's a reference to the requirements, the software requirements that are used to run the model. You need this in order to build the software environment. So for instance, if you want to deploy on Kubernetes, Kubernetes needs a Docker container. This Docker container is built by using the Conda YAML definition file for building the Python environment within a Docker container. Now, the model pickle file that's the model itself with the model weights, and any additional artifacts that you want to package with your model can be put here as well. So now I want to go through the entire machine learning lifecycle by showing you. If there's any questions, I don't think so. So I will now demonstrate the machine learning lifecycle by using Azure Machine Learning and Mlflow. I will start with showing the machine learning workspace. So this is a demo machine learning workspace that I've built. This is the interface. This is a way that you can manage all of your machine learning assets. You have links to your notebooks, You have links to your data, to your jobs, to your components, all of the things that I've mentioned. You can link to here. I'll start by showing you how to manage your data. I have an example data set sitting here in a Azure storage container. So this is just a path on my storage container with a lot of CSVs holding sales data for fake sales stores. And if I want to build a forecast model using this data, I register it in Azure Machine Learning. So this is a Regis data set with version 1. I'm going to use this in a job. So doing that, I start by working in a notebook. My notebook runs on Azure Machine Learning Compute. The first thing that I've done is I have made sure to clone my Git repository on the Azure Machine Learning file system. So what you see right here to the left is the Azure Machine Learning file system. All of the compute resources. I'm working on a compute instance right now. This is a compute instance that's running, which is assigned to me. All of these compute instances come with Git installed. So you can just do Git clone. And as long as you have access to your repository, you can clone your repository right here. I have a notebook inside my repository that I'm running over here. I can run the cells in this notebook and then start by exploring my data. I'm pulling the data right now from the blob container that I've showed you. I can start working on my transformation code in the notebook, and then as soon as I'm satisfied with my transformation code, I start working on my pipelines. So I have a number of experiments here. Actually, there's only just one, and I've defined 3 components and a pipeline that trains a model for me. Well, I could run the notebook and train a model. Training the model takes quite a while. So what I've done instead is I just ran the pipeline this morning. I ran it from Git because since all of this is stored in Git, we've also made sure that all of the pipelines can be run from Git. So this is an integration pipeline that's running in my DevOps environment. What this does is that this deploys the Azure Machine Learning environments that I've defined in my Git repository. It also deploys all of the components, and it schedules and runs all of my machine learning pipelines. So all of the environments that are listed in the Git repository here, this XGBoost example environment, for instance, is registered into my Azure Machine Learning workspace. The components that I'm using in all of my pipelines are also registered. And the job that I ran this morning is logged here. You can see all the 3 components that I use. My data preparation script is executed here. My model is trained and my model is evaluated. When I look at one of these components, I see that all of the information is logged. It also logs the Git commit that was responsible for the code, so that you can make sure that afterwards, when a component is failed or when it executes, that you know what code was responsible for running this specific component. Finally, one of the models, the evaluate model, will run and register my model. So when I go to the model overview, I have my model that was trained this morning. I can see what job was responsible for producing the model. This is how the entire operation is run from Git. So that's Azure Machine Learning using MLOPS. This is a small example. This pipeline will only train a model. You can also have pipelines that use a model in order to consume a model and provide the forecast for you. This is not an example of that. This is just an example of how to train a model. If you're interested in having a look at the code, having a more in-depth look at the code, a lot of examples are available by just Googling Azure ML examples. This is a Microsoft repository, of course. Microsoft put a lot of tutorials and examples in this repository. So if you're interested, just Google Azure ML examples, and a lot of these pipelines are stored right here. So if there's any questions, I have some time to spare. But if not, then thank you for attending, and we're at the end of my talk.